Okay, I'm going to talk about a paper. This is game theoretical interactions of moving agents. This is Wenjian Yu and Dirk Helbing. Dirk Helbing is a complexity person. He runs complexity, like a website where he does a lot of demos of complexity concepts. So I think it's complexity explainables or complexity something like that. And so he's got some interesting, usually he's engaged in some interesting work. He's at ETH Zurich, so that's where the authors are located here. This is from the arXiv, and it talks about game theory and some of the things about agentive systems or multi-agent systems. So I thought it would be kind of interesting for just thinking of what they're doing here. So the abstract reads, game theory has been one of the most successful quantitative concepts to describe social interactions, their strategic aspects, and outcomes. Among the payoff matrix quantifying the results of social interaction, the interaction conditions have been varied, such as the number of repeated interactions, the number of interaction partners, the possibility to punish defective behavior, etc. While an extension to spatial interactions has been considered early on, such as in the game of life, recent studies have focused on effects of the structure of social interaction networks. However, the possibility of individuals to move and thereby evade areas with a high level of defection and to seek areas with a high level of cooperation has not been fully explored so far. So what they're referring to here is they're referring to things like the prisoner's dilemma, where in the prisoner's dilemma, you have maybe like a group of people, could be 2 or 3 people, who are engaged in some sort of activity, maybe a conspiratorial activity. The idea is maybe they've committed a crime together. And then when the police interview them, they interview them both, one at a time. And they want to know what they each know. And they also want to see if any one person will defect and flip and tell the police about the activities of the other people. So they want to see if they can get some sort of defection from the group, which exists in conflict with cooperation within the group. So the group can stick together and no one individual can talk to the police and give them any information. Or one person can defect and usually, they get their sentence commuted or something, so they get a benefit for themselves, but then the group suffers because the other 2 people get outed or thrown under the bus, as they say. So that's kind of where they're going with this. They're kind of using the prisoner's example, or the prisoner's dilemma example, without actually mentioning it by name. So the idea here is that they're extending this to individuals moving around a spatial array. And so you have different regions of the spatial array where there's a high level of defection, and you can move to places where there's a high level of cooperation. And when you move to places with a high level of cooperation, it selects for, or it encourages group cohesion. Because obviously, if you don't have cooperation, if everyone's in it for themselves, that's not good for collective behavior. And so this is where you have a bunch of agents on a grid or on some sort of spatial surface, and they're moving around, and they're trying to find places that are sort of key for cooperation, and they're trying to evade areas that are centers of defection. That's basically the idea. And so this contribution presents a model combining game theoretical interactions with success-driven motion in space, and studies the consequences that this may have for the degree of cooperation and the spatiotemporal dynamics in the population. So again, this is a multi-agent simulation where there's this imperative, and you can look at the strategies employed by any one agent. And you can look across the agents and see that they tend towards the strategy of encouraging cooperation and minimizing defection. But they all do this independently. So they all make independent judgments about this. And it's reflected in the movement patterns of the agents. So they're moving to places where these things are sort of highly rewarded. So there might be one region of the space where cooperation is rewarded. There might be other regions of the space where defection is rewarded. So whatever the payoffs are for those different strategies in different regions of the space determine how these agents move. It is demonstrated that the combination of game-theoretic interactions with motion gives rise to many self-organized behavioral patterns on an aggregate level, which can explain a variety of empirically observed social behaviors. So, we're looking at how these behavioral patterns emerge in space. So as the agents move, they move to these areas and they, form groups, they form collectives. And then we want to be able to analyze that at the end of our simulation and see what the outcome is. So getting into the paper, macroscopic outcomes in a social system resulting from interactions between individuals can be quite different from anyone's intent. For instance, empirical investigations suggest that people prefer different types of neighborhoods based on their self-identity. Someone could think that integrated neighborhoods should be widely observed, but empirically this is not true. One rather finds segregated neighborhoods, such as separate urban quarters, which also applies to people with different social and economic backgrounds. This is actually building off of showing segregation simulations that he ran in the 60s. And so this is an old problem in urban sociology, looking at different people belonging to different social groups and whether they move into the same neighborhoods or they move into neighborhoods with people of different backgrounds. There's this urban ecological social distance tradition in sociology and the individual preference tradition in economics. So basically, you're looking at this difference between the sociological lens and the economics lens. The main idea of social distance theory is that differences in culture and interests between social groups are reflected by a separation of the residential areas. And then so this is, yet the role of social distance and individual preferences is questioned by the studies of the American urban housing market, which suggests that racial discrimination and prejudices are the primary factor of residential segregation and concentration of poverty. There are 3 stages in the housing market transaction, which is where, they kind of go through, the information about available housing units, terms and conditions of sales and financing assistance, and then access to units other than the advertised unit. In each stage, the housing agent may behave in a discriminatory way, withhold information from customers, and discourage them. Therefore, the access of minority customers to housing is severely constrained, while the theory of preference-based dynamics assumes that people can relocate freely according to their own preferences, which fails to reflect the real relocation dynamics. And so this just kind of goes through the relevance of this kind of study that they're going to do. So then we can look at this in game theoretic terms. We can look at migration, game theory, and cooperation. So in game theoretic terms, this movement to a more favorable neighborhood could be reflected by a higher payoff to persons who moved, called migrants, in the following way. Migratory behavior aimed at higher payoffs is called success-driven motion. So this is where you're moving to get a higher payoff. And this is what they call success-driven motion, and there's some citations to back this up. As we will show in later sections, success-driven motion can reproduce residential segregation and some other observed phenomena of population dynamics as well, like population succession, which is an example of which is cycles of changing habitation. You see this in ecology with different species in ecosystems. We will also study how a change of the spatial population structure can affect the level and evolution of cooperation in a population. It could be thought that natural selection, implying competition between individuals, would result in selfish rather than cooperative behavior. Nevertheless, cooperation is widely observed also in competitive settings from bacteria and in animals as well. Game theory has been regarded as a powerful framework to investigate this problem, as it can be used to quantify the interactions between individuals. And so there's a mathematical formalization to this. So the mathematical description of of selfish behavior tendencies is often based on the prisoner's dilemma game, in which the reward R represents the payoff for mutual cooperation, while the payoff for defection or cheating on both sides is reflected by the punishment P. So this is where, the idea that if you have two prisoners who collaborate on a crime and they get interviewed individually by the police and they have to, tell the police what they know and they get a reduced sentence, but that involves, identifying the other person and betraying the other person's trust and all of that. So the punishment is where the individual flips and gives the police that information. Now the idea is that's punishment because both prisoners would do this, whereas the reward is when both prisoners keep their mouths shut and the police get no information. So that's the way that's structured in the prisoner's dilemma. So you have reward, you have punishment, and you have maybe some state where one prisoner flips and the other prisoner doesn't. So this is actually another optimal state where one prisoner gets sort of the reward and then the other prisoner gets the punishment. I mean, it's optimal for the one prisoner, but it doesn't encourage social behavior or pro-social behavior. Unilateral cooperation will occur in the so-called sucker's payoff S, where the defector gains T, the temptation. This is what I was describing before. Given that inequalities T is greater than R is greater than P is greater than S, so temptation is greater than reward, is greater than punishment, is greater than the sucker's payoff, and 2R is greater than T plus S. Defection is tempting and cooperation is risky. So you're tempted to defect, and it's risky to cooperate because you don't know if the other person is also cooperating or if they're defecting. So that defection is expected to be dominating, although mutual cooperation improves the average payoff. So the payoff is better when you cooperate, but there's no way to know that other people are cooperating. So you typically will defect, and there's a limited reward there, but at least you'll get that reward. That's basically the way that the prisoner's dilemma is structured. So that's what they're using as a way to model the spatial segregation problem. In a well-mixed population where an individual interacts with all the others, a defector's payoff is always higher than the average payoff, which leads to a prosperity of defectors. So defection, of course, pays off higher than the average. And so that actually discourages cooperation. But sometimes you can have, and a well-mixed population is just basically where everyone's interacting with each other. So it's, there's no preferential individuals interacting with one another. Maybe they have a very varying amounts of trust in each other. So it's not, that's all controlled for. This is, of course, not a spatial game. It's just kind of in a regular setting where you have these interactions going on amongst agents. So when we add the spatial dimension, we should expect that maybe the dynamics will look different. In an evolutionary setting, as it is described by the replicator dynamics, and that's where we have replication of agents and their states. Only those strategies that generate above average payoffs have the chance to spread. Therefore, from an evolutionary perspective, there will be no cooperators in the end, which contradicts the observed cooperation in reality. So we expect defection to dominate, and we expect no cooperation, even though in reality we observe cooperation. A variety of mechanisms have been proposed to explain the considerable level of cooperation observed under certain circumstances. These include kin selection, direct reciprocity, indirect reciprocity, group selection, and network reciprocity. In particular, it is interesting that the spatial population structure can significantly change the level of cooperation in a population. While there could be a coevolution of social structure and cooperation due to migratory behavior, this subject has not been well studied in the past. So that's what they're going to do here. So they go through some real-world data from different urban areas. They're looking at the city of Chicago and the movement of immigrants in the early 20th century. And they see that in that data set, they have different types of succession processes of specific cultural groups, where you have sort of an initial settlement, you have conflict, you have recession and reorganization. So you have groups that move into a certain area, other groups will kind of move into the same area, there will be conflict, and then there will be resegregation of those areas by that group. So the invasion is sort of when new groups move into an area and then the dynamics change. So the invasion then can be initiated by a few pioneers who manage to enter a new area dominated by older residents. For example, people will move to an area and then, have social connections, and that, other people will move into the area, and then there will be this succession. So that's the idea. And then, of course, this assumes that everyone in a certain group, that they have this affinity with everyone in that group. So that's kind of the assumption being made here. So following the initial invaders, invasions can happen on a much larger scale, in particular if housing prices go down. So it's like dependent on housing prices, at least in this data set. Then previous residents who want to sell their houses at a good price are eventually replaced. People may even move without reasons, just following a trend of what others do, which is a kind of collective herding behavior. So this is an important point, is that sometimes these decisions are made sort of consciously, and sometimes it's just kind of following some trend that you're observing. Because sometimes you know what the payoff is, and sometimes you don't, but you have this sort of signal that's, maybe people are cooperating, maybe people are defecting, and you're trying to get the best payoff. Accompanying this replacement process, the changing composition of the population may cause conflicts due to incompatible cultural values and prejudices. So it's, again, is it conscious or unconscious in terms of how the strategy is followed. So this results in a turnover, and you can see these spatial dynamics play out. So this is, again, something we can model computationally. Spatial games based on lattices would allow for one to study such effects. In conventional spatial games, individuals are uniformly distributed in the simulation area and change or repeat their strategies following a certain updating rule. So an individual is assumed to unconditionally adopt the most successful strategy within that neighborhood. On the one hand, this creates typical spatiotemporal patterns. On the other hand, spatial structures play an important role in the maintenance of cooperation. So this is where, you kind of have certain assumptions of the payoff matrix, and that determines what the spatiotemporal pattern looks like. But also, if you have a certain spatiotemporal pattern that exists, it sort of sets the terms of the payoff structure. So it may be more likely that you cooperate or less likely that you cooperate, depending on what the existing spatial structure is. So if you already have a segregated neighborhood, then it's like probably the cooperative imperative there may be higher. And so that's kind of the idea here. In the iterative prisoner's dilemma, for example, clusters of cooperators are beneficial to cooperators, while the evolving spatial structure in the snowdrift game, which is a variant of prisoner's dilemma, and that's a game where the way this game works is that you have two snowplows, and they are plowing a road from different ends. This is like in a mountainous area. And the snowplows come to a certain point where they meet. And the idea is, do they cooperate to move the rest of the snow out of the way? Or do they not cooperate? And so this is kind of, you can model, sometimes these games are based on things like idiosyncrasies in the world. And people observe this thing and they kind of name a game after it. So, that's what the snowdrift game is. It's just a variation on the prisoner's dilemma. But it has very similar dynamics. And so, we can look at that game and, it's a little bit different than the prisoner's dilemma because there's an explicit spatial structure in it. And so the snowdrift game can inhibit cooperation. So when you get a different type of game or structure of a game, it can have different dynamics. Conventional spatial games, however, neglect the possibility of individuals to move or migrate, although mobility is a well-known fact of daily social interactions. We will see that the movement of individuals, or what we might call population succession, can change the spatial structure of a population significantly and influence the evolution of cooperation dramatically. So this is where we get into spatial games with mobility. So these are what we call mobility games. And so we have different ways to classify these. We have 8 ways to classify them. Number 1 is that mobility may take place in a physical or geographic space with multiple dimensions, or it can occur in an abstract space like something like opinion space if we're looking at sort of different types of epistemic models. Rather than a grid, we might have a network structure like a friendship network, and we can play the game there. Number 2 is that one may distinguish between games with continuous and discrete motion. So, whether the movement is sort of a trajectory or whether it's across a grid and has different number of steps. The first ones may be considered as particular cases of differential games. So continuous games are sort of differential games where you can derive differentiable functions and do things like calculus on them. And those can be called motion games. The second ones will be named migration games and can be implemented, for example, in terms of cellular automata. So this is where we have the grid, where we have movement across that grid that's more categorical in nature. Number 3, the mobility game may be deterministic, i.e. noisy, influenced by fluctuations, or having this sort of stochastic property. So it can be either deterministic or stochastic. Such noise can be introduced by stochastic update rules, and there are different ways you can kind of think about setting up that aspect of the game. Number 4, multiple occupation of a certain location may be possible, allowing for the agglomeration of individuals, or it may be prohibited. In the latter case, spatial exclusion requires spatial capacity constraints and or the respect or protection of some private territory. So this is, again, the dynamics we saw earlier where we were talking about different types of invasions of space and, kind of people's response to that behaviors. Whether they all kind of move in mass or they kind of move as sort of a signal that they see in the environment, or they don't move at all. Number 5, in mobility games of spatial exclusion, empty sites are needed. Therefore, the density of free locations is a relevant model parameter. So if you have a very dense grid where no one can move, of course, then you can't really have a mobility game. If you have a very sparse grid, then people can move, or agents can move. And if you have a moderate grid, sometimes you have spatial constraints. So it's like they might have, it might be that there's an imperative to move, or, there might be a place where you can get a higher payoff, but you can't move because that area is jammed. So you take the next best payoff. Number 6, the frequency, rate, or speed of mobility may be relevant as well and should be compared with other timescales, such as the frequency of strategy changes or the average lifetime of a spatial cluster of individuals. Depending on the specification of the game, after a transient time, one may find everything from chaotic patterns up to frozen patterns, which can be expressed by a viscosity parameter. So in spatial arrays, we usually have this thing called a jamming phase transition, where you have the movement of things through a space, and then sometimes they're dense enough so that at a critical parameter value they jam. And that means that they go from this sort of motion to this frozen state. And it's totally dependent on density. So if the density decreases, movement starts again. But there's usually this change in state based on this critical parameter value of the ability to move. Mobility, number 7, mobility may be random or directed. So it may be success driven or it might be random. And so if it's random, then the agent isn't looking for the best payoff, they're just moving around. If it's directed, then they're looking for a better payoff, and that's success driven. Although they may not be finding success immediately, they're moving towards a higher level of payoff. Directed mobility may depend on the expected payoff in a certain time point, iteration, or it may depend on the cumulative payoff, which is the accumulation of payoffs over time, over iterations. And then number 8, if age, birth, and death are considered, one speaks of demographic games. So you can actually play these games with agents that are maximizing their payoff over time, or you can have replicators where agents die and new agents are born, which are descendants of the old agents, and they kind of accumulate this payoff, and the new agents can have different sets of epistemic conditions or values, and they can change their behavior accordingly. And sometimes the payoffs change as well. So that would be a demographic game. So they're focusing on games with success-driven migration in two-dimensional geographic space. Furthermore, we will assume simple strategies such as all cooperate or all defect, no memory, no forecasting abilities. So this is an example of a discrete game where you have this focal individual that's an empty circle. You have red individuals and black individuals, or these red and black pawns or agents. And you have an equal number of each. So you have 8 neighbors of this focal individual in 2 different states. We assume that all individuals prefer places that can provide a higher payoff. However, movements are restricted by mobility and the factors implicated in mobility, and the number of free locations, as one can only move to empty places, and in a residential context it would be if they can afford to move to that place. So there may be places that have different accessibility values. In a residential setting it would be how much does a place cost. In this case it's just kind of like how accessible is that spot on the board. In our model, the mobility is reflected by the migration range M, which can be assumed constant or as a function of cumulative payoffs. So you can move farther if you have more of a payoff that you can either attain or have had in the past. So movement may be specified proportionally to the distance moved, and beta is a constant in this equation here. When the migration range M is restricted by the cumulative payoff, one may set the migration function here. So this is the example here where you have a focal individual and they could have neighborhoods of different sizes. You have a Moore neighborhood of range 1. A Moore neighborhood is every neighbor that's either adjacent, every neighbor that's adjacent in one movement to the focal cell, it's either diagonal or cardinal direction. In a Moore neighborhood of range 2, you have 2 cells. So the neighborhood is 2 cells deep in all such neighbors. Okay, so that's kind of an example of what we're doing in a discrete game with a Moore neighborhood, and it's very similar to what we see in a cellular automata. And so the expected payoff for individual I applying strategy small I at a free location x prime within the migration range that'd be calculated with this function, where you account for the strategies of the individuals located within a neighborhood centered at location x prime. Here we assume that the individual can determine this value by testing a neighborhood n prime by means of some kind of fictitious play with its residents. So in other words, you can figure out what the payoff is and what the value of doing something is by communicating with people or agents, or you can get a kind of a gist of what the other agents are doing by observation. So that's the idea. You're just getting information from the surrounding environment. All individuals are assumed to maximize the expected payoff by migrating to the place that promises the highest payoff. Consequently, the payoff at the new destination for I is expected to be this function here, where we maximize for the payoff, where A represents the area within the migration range M around xi. In our model, individuals decide to move if the expected payoff at the new position satisfies the short-term cost-benefit condition here, where your payoff is greater than not moving. If we assume that the cost of each movement is small, and the new neighborhood yields a comparatively high cumulative payoff over the time period the individual stays at that place, then the cost of movement can be neglected. But usually there is a cost of movement that is something to account for. Finally, if 2 or more places promise the same maximum payoff, we assume that the individual will choose the closest one. If both the payoff and distance are the same, then the individual will randomly choose one of the closest locations in our simulation. Since all the other individuals also seek new places that can increase their payoffs, neighborhoods may change quickly, and the resulting payoff may fall below the expectations before the move during this fictitious play step. So sometimes you have this sort of random, or you have this turnover, and sometimes you don't. And then the question is, why is that? And so sometimes it has to do with the payoff structure, sometimes it has to do with where other people can go, and there is this aspect of kind of figuring out what everyone else is doing, what payoff everyone else is getting. And then in human dynamics, like in the case of residential neighborhoods, you have this aspect of identity as well. And then we talk about learning. So learning allows individuals to adapt their behaviors in response to other people's behaviors in an interactive decision-making setting. Basic learning mechanisms are, for example, unconditional imitation, best reply, and reinforcement learning. So we want to include a learning step here. So we have this observation step or fictitious play, then we want to learn from that. So we can use different types of kernels, I guess, for learning. We might just have imitation, where you just copy other people, and that results in a very rudimentary type of set of dynamics. You have best reply, which is, okay, out of these options, what's my best option? And then reinforcement learning, where you select the best policy. And there are other types of ways to do this as well. Now, for our open source sustainability project, we kind of have this sort of spatial structure in our agent-based models. And there's no explicit spatial structure in open source communities, except that you do have these sort of dynamics where you have to kind of figure out what other people are doing and coordinate with that. So we use reinforcement learning. We also use active inference, and there are other ways you can do this as well. with personality models or with other types of models. So this is kind of one of these things for multi-agent systems. You have to kind of figure out the best way to model it and what gives you the best set of conditions. So they go through unconditional imitation, which is where you just copy the behaviors of others. It results in a lot of hurt. It overemphasizes herding as a high payoff strategy. Reinforcement learning is kind of a backwards looking learning behavior, i.e. people tend to take the actions that yielded the highest payoffs in the past. So if something has yielded a high payoff in the past, you replicate that in the present. This is one of the things about reinforcement learning that is maybe a problem for a problem like this. And that is, it doesn't allow for new or novel solutions to occur. So if you kind of, make the same mistakes in the past, you replicate those mistakes, you keep making them. It's worth thinking that reinforcement learning was originally kind of a behaviorist model for behavior, and they did a lot of the experiments in rodents. And so it was always about, can you remember where the food is, basically. And so that's where reinforcement learning really kind of got refined. And then, of course, it was applied to artificial intelligence, where it's very good at sort of building sort of memories or building learned locations or learned things. But it's not necessarily very good at incorporating new information. So this is kind of a point that we need to think about. And then, of course, there are other types of learning models we can use. They talk about this best reply, which is where you choose your strategy based on the expectation of what others will do in a way that maximizes their payoff. So you're trying to it's almost like a theory of mind type of thing, where you're trying to figure out what other people are doing and how their payoff is working, and then how your payoff should work. So you're forecasting other people's forecasts, and then you have to have a belief about how other people behave. So you have to have sort of a theory of mind here. And so that's what best reply is. We can think of other models as well for dealing with, this problem of an agent trying to figure out what other agents are going to do. So in this model, players can only interact with the 4 nearest neighbors and adapt their strategies by unconditional imitation. And so this is where they run the simulation. And here's some results. So in figure 3, they have these 49 by 49 grids. They show the results for migration only, imitation only, and migration and imitation. So this is where, I guess migration is where they're actively seeking a higher payoff. Imitation is where they're just imitating their neighbors. And then you have both. And when you have both, it looks like you're getting sort of the best result. Let's see. So, let's see. They don't really mention it in the legend. Let's go down to the bottom here. So yeah, I guess the idea here is that the mix of those two things, imitation and migration, are the best. Here we've examined how individual preferences can change the spatial population structure in a very simple social system, considering migratory behavior. The revealed social process can, to some extent, reflect the dynamics of population succession in urban areas. This corresponds to case B in figure 3. Consider the payoff matrix for that figure and imagine that an individual of group 1 happens to be located in the neighborhood of group 2. So when they're talking about B, they're talking about this strip of results. So migration and imitation is here. It seems to give the best result. B actually models residential segregation in the data set that we talked about. So that's kind of what they're referring to here. So if we consider the payoff matrix that generated that figure 3B, and imagine that an individual of group 1 happens to be located in that neighborhood of group 2. For the previous residents, this may not change a lot. However, it attracts other members of Group 1 who are not yet living in a neighborhood of Group 1 individuals. This can trigger collective migration of other Group 1 members. Since interactions between members of Group 1 and 2 bring positive payoffs only for members of Group 1, Group 2 will finally leave for new places. Of course, this process repeats, just like the circle of population succession that we talked about earlier. One may notice that here we do not differentiate the intention to migrate and the actual migratory behavior. So there's no intentionality that's separated from the payoff. In daily life, however, the movement of people is restricted by many more factors, such as wealth and time, so people do not migrate often, even if they are motivated to move. So sometimes you can't move because you don't have the space on the grid. Sometimes there are other things you could model, other factors in the mind of the agent that you could model. They don't do so here. In our simulations as well, migration activity after a few iterations is small. So starting with a high migration rate due to the artificial choice of a random initial distribution, the migration rate quickly drops to a low level. Of course, other factors determining migration can be easily added to the above proposed framework of migration games. And so then they link this back to the prisoner's dilemma and the promotion of cooperation. So this is where in figure 4 they show the migration-only case with the imitation-only case corresponding to m equals 0 and the combined imitation and migration case with m equals 5. In the imitation-only case, the proportion of cooperators is greatly reduced. So figure 5 is down here, and it's a similar thing to what we saw for figure 3. This is migration only where m equals 5. Imitation only where m equals 0. This is migration, and then migration and imitation, m equals 5. So you see that that's what they're referring to there. So in the imitation-only case, the proportion of cooperators is greatly reduced because you don't know what you're cooperating with. You're just imitating other people. You don't really know what the payoff is. However, the combination of migration and imitation strikingly promotes the level of cooperation. Our explanation is that when individuals have mobility, cooperative clusters are more likely to be promoted in the presence of invasion attempts of defectors. We can see that in the migration-only case, cooperators manage to aggregate and to form clusters. Although defectors attempt to enter cooperative clusters, they finally end up at the boundaries of cooperative clusters as cooperators split to evade defectors and re-aggregate in new places where defectors are excluded. And so in the prisoner's dilemma, it is guaranteed that 2r is greater than t plus s, which means that the attractive force between cooperators is mutual and strong, while the interaction between a cooperator and a defector leads to a unilateral attractive force where t is greater than 0. When 0 is greater than s, a cooperator replies to defectors even in a repulsive way. Therefore, defectors are less successful in joining or entering cooperative clusters than cooperators are. So there's almost this attraction-repulsion dynamic with respect to these different strategies. So when a strategy is stronger, you have this attractive force. When the other factor is stronger or weaker, a cooperative force is preferred. And so they kind of get into how these dynamics work. And let me get to let's get to the conclusions. We have introduced the concept of migration games by considering success-driven motion. Migration games can easily reproduce macroscopic stylized facts of various social phenomena based on individual actions and interactions. Typical examples are population succession and residential segregation. These aggregate outcomes emerge from interactions between individuals in a non-trivial way, and a theoretical analysis allows us to qualitatively understand the relation between microscopic interactions and the emergent macroscopic phenomena. For the prisoner's dilemma, we have shown that self-organized cooperative structures can promote the level of cooperation. Moreover, we have verified that any enhancement of cooperation by success-driven motion is robust to different kinds of noise. We even find that moderate noise levels can promote the cooperation level further. The underlying mechanism is that in the migration game, success-driven motion will monotonously increase, which means linearly, the total payoff in the noiseless system, which however can lead the system into a locally optimal state. The effect of noise can drive the system out of local optima towards the globally optimal state. And then they talk a little bit about the links to sociology and some of the other things that we originally talked about. It would be natural to extend migration games in order to study the coevolutionary dynamics of population structure and urban growth. In the long run, we hope this will contribute to a better understanding of planning and population dynamics in a city.